Right now, your phone knows roughly where it is, even with GPS completely switched off. The cell network on its own can place you within a few hundred meters, and often a lot better. No satellites, no GPS chip needed. It feels like magic, but it's really just geometry and a little physics. So let's build the whole idea from scratch, starting with one tower and ending with the actual math. Here's the setup. Scattered across the city are cell towers, and your phone is constantly in touch with the nearest ones. Each of those links carries a small clue about where you are. On their own, the clues are vague, but combined they get surprisingly precise. The network's whole job is to take these invisible radio connections and turn them into a single dot on a map. Let's start with the simplest case, just one tower. Say your phone is connected to this one, Tower A. Right away, the network knows something useful. You must be somewhere inside Tower A's coverage area, because that's the only place its signal reaches. This is the crudest way to locate a phone, and it has a name, cell ID. It's literally just asking which tower you're talking to. Fast and universal, but, as we'll see, pretty rough. And it is rough. A single cell can be a few hundred meters wide in a busy city center, or stretch several kilometers across out in the countryside. So cell ID might only tell the network you're somewhere inside a huge circle. Better than nothing, but nowhere near a pin on a map. To really narrow it down, we need one more number. Not just which tower you're near, but exactly how far from it you are. So suppose we measure that distance, and it comes out to about 1 kilometer. Watch what that single number does. If you're exactly 1 kilometer from the tower, you can't be just anywhere anymore. You have to be sitting on a circle 1 kilometer in radius, drawn around the tower. We've gone from a giant blob to a thin ring, a huge improvement, but the ring still wraps all the way around, so you could be anywhere along it. One distance isn't quite enough. So we bring in a second tower and measure your distance to it as well. Draw its circle. Now here's the key idea of the whole video. Two circles can only ever cross in two places. So your position has to be one of those two crossing points and nowhere else. In a single step, we've gone from a whole ring of possibilities down to just two suspects. And a third tower finishes the job. We measure your distance to Tower C, draw its circle, and it passes through only one of those 2 points. The other is ruled out. 3 towers, 3 distances, all meeting at a single spot, and that spot is you. This is the heart of it, and it has a name, Trilateration. 3 measurements, working from distances. Now a quick myth bust, because this trips up almost everyone. People always call this triangulation, but technically that's the wrong word. Locating something using distances, these circles, is called trilateration. Triangulation means something different, using angles, the actual direction a signal arrives from. A few systems really do use angles, but cell networks mostly work from distance and timing, so trilateration is the honest word for it. Terminology sorted. Now for the real question, where do those distances actually come from? Here's the beautiful part. Radio waves travel at the speed of light, about 300 million meters per second. Put another way, a signal covers roughly 300 meters in a single microsecond, 1/millionth of a second. So if the network can measure how long a signal takes to travel between the tower and your phone, it can turn that tiny travel time straight into a distance. Just multiply time by the speed of light. Distance equals speed times time, the formula from school, running at light speed. In real networks it works like this. The tower measures the round-trip delay of your signal and sends back a value called the timing advance, telling your phone to transmit a little early so everything lines up. Each step is worth about 550 meters. There's also a rougher backup using signal strength. The weaker the signal, the farther away you probably are. And because most towers split their coverage into sectors with directional antennas, like these, they even know roughly which direction you're in. There's one catch, though. Your phone doesn't carry an atomic clock, so measuring exact travel time is genuinely hard. So modern networks use a clever trick. Instead of absolute time, they compare the difference in arrival time between two towers. A fixed time difference doesn't trace a circle, it traces a curve called a hyperbola, and every point on it fits what the towers measured. Do it for a second pair of towers, and the two curves cross at exactly one point, U. This is called TDOA, or multilateration. Alright, let's actually do the math because it's simpler than you'd expect. Each tower gives one equation, and it's just the equation of a circle, x minus the tower's x squared, plus or minus its y squared equals the distance squared. Your position, x and y, is the only unknown. 3 towers give 3 equations for 2 unknowns. That sounds like too many, but it's a good thing. The extra one cancels out noise. Now here's the slick move. Take any 2 of those circle equations and subtract one from the other. When you do, the x squared and y squared terms cancel out completely, and you're left with a plain straight line equation. Do it for 2 different pairs and you get 2 lines, and 2 lines cross at exactly one point. So the whole problem collapses from scary circles into 2 simple linear equations you can solve in a few lines. Out pops a single coordinate, and that's your location. Of course, the real world is messier. Every measurement carries some noise, so each circle isn't a perfect line, it's really a fuzzy band. And when fuzzy bands overlap, you don't get a clean dot, you get a small zone of uncertainty. Signals bouncing off buildings, an effect called multipath, make it worse, and so too few towers or badly placed ones. But the fix is intuitive. Add more towers and better timing, and all those fuzzy bands overlap in a much tighter region, shrinking the uncertainty. That's why a dense city, packed with towers, can locate you within tens of meters, while in the countryside, where towers sit kilometers apart, the same system manages only a few hundred. More towers, better geometry, a sharper fix. So let's put the whole journey back together. One tower puts you inside a cell. A distance from that tower puts you on a circle. A second and third tower cross those circles at a single point. Trilateration. The distances come from timing because distance equals speed times time, running at the speed of light. Modern networks refine it with time differences and hyperbolas. And in the real world, noise turns that point into a small zone. So the more towers in range, the sharper the answer. No GPS, no satellites, just radio geometry and a stopwatch. So next time your phone finds you with location off, you'll know exactly how.